So in this video, we're now going to talk about electrostatic boundary conditions, or what has to happen when we have two materials with two different permittivities touching each other. All right, so we're going to derive a few things called boundary conditions. And so let's consider, here I have a line. On one side of the line, we're going to call this material 1. Let me actually draw the line horizontal to be consistent with the notes. This is going to be material 1 on the top side and material 2 on the bottom side. All right, material 1, let's say it has a permittivity epsilon 1, and material 2 has a permittivity of epsilon 2. All right, now what boundary conditions are going to do is they're going to help us relate three things to each other. The first is going to be the electric field on the first side, right? So we may have an electric field on this side. Let's call it E1. There may also be an electric field on the second side, E2. And the other thing that there might exist is charges that could build up right on the surface between these two materials, particularly if either material is conductive. Then there may be surface charges that build up. And we're going to call that rho S, right? Where rho is the charge density along the surface. It's going to have units of coulombs per meter squared, right? So boundary conditions are basically going to help us directly relate these things to each other. Now, in order to do this, I'm going to define a vector called n. I'm going to draw it in red right here, right? N is a unit vector. So it has length 1. It is perpendicular to the boundary. And it points, by definition, by convention, into material 1. All right. So with that, let's just write down what boundary conditions are. Now, in order to derive this, I'll sort of give you the trick. You can basically draw a little surface like this, what's called a Gaussian pillbox, around this surface and solve for the fields and the charges around it. And you'll come up with a couple of different relationships. I'm not going to go through the details of how to do this, but you can find this in any physics textbook, and I have a little more of a detailed description in the notes. So the two boundary conditions are going to look like this. First, I want to take this electric field and I want to decompose it into two pieces. Okay, so we're going to have this component right here. I'm going to call this E1 perpendicular, right? It's perpendicular because it's perpendicular to the boundary. The boundary is to the side, and the E1 perpendicular is up and down as I've drawn it. The other component, which could be in this direction, I'm going to call this E1 tangential. Right, tangential because it's tangential to the boundary normal, to n. All right, we're going to do the same thing for E2. All right, so this is going to be E2 perpendicular and E2 tangential. Right, so whatever the vectors we have, E1 and E2, we can decompose that into vectors that are basically along the surface and through the surface, right? Those are the two things. Perpendicular is through the surface and tangential is along the surface. All right. And one thing that I want to recall for you that we talked about earlier is that the electric field from a sheet charge looks like this. It's E equals rho S over 2 epsilon. And there's a plus or minus there because it's either pointed, toward or away from the sheet of charge. In particular, if you've got charges like this that extend infinitely far in all directions, you're going to get electric fields that flow away from it, which means it's upwards on the top side of this sheet, and it's flowing downwards away from it on the bottom side of this sheet, right? So that's what you're going to need to sort of figure out how the charge density fits into this. What's important to note is that the difference in the electric field from one side to the other, right, you can look at that as delta E, is simply equal to rho S over epsilon. Right? Another way to look at it is that if there is charge built up, then the delta D on this side is going to be equal to exactly the charge density. That across this boundary, we're going to get a change in the electric flux density that is precisely equal to the charge density that's built up at the surface. And specifically, we're talking about the component that is in this direction. That's the only component that's going to be impacted by this charge density, because the charge is stratified horizontally. And so it only creates electric flux density that's up and down. And so mathematically, we're going to write this in the following way, that D1 perpendicular minus D2 perpendicular equals rho S. This is actually a restatement of Gauss's law, right? In particular, the grad dot D equals rho V. You can recast this and figure out that D1 perpendicular minus D2 perpendicular equals rho S. That the component of the electric flux density that is through the boundary is only going to change if and only if there is charge built up at that boundary. And if there's charge built up at the boundary, then the component of the D field that is through the boundary is going to have a step change right at that boundary. Right? We can state this with electric fields simply by applying the fact that D equals epsilon E. So we can also write this as epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular equals rho S. But there is another way to state this, which is a little more convenient, which is that if we take the normal vector n and we take the dot product of D1 minus D2, it will equal to rho S. These are equivalent. What's more powerful about the one on the right is that it's not dependent on coordinate system, right? If I set up my coordinate system with x going this way and y going that way, then it's pretty easy to take my electric field and decompose it into x and y, because those will be the same as tangential and perpendicular. But if I didn't have that coordinate system, if I had, x oriented this way, and I had y oriented that way, then x and y would not immediately correspond to the tangential and perpendicular components. And that would make it difficult to set that up. But if you apply this form right here, where the n vector dotted with D1 minus D2, then whatever coordinate system you're using, it's going to give you the same answer automatically, right? So this can be a little more convenient and a little more powerful for more general coordinate systems. So I recommend sticking with this one. All right. The other boundary condition that we're going to talk about here is, let me go back to black. And that's that the component of the electric field in the tangential direction is going to be the same on both sides. So E1 tangential minus E2 tangential equals 0. We can also write that in a more general form as n hat crossed with E1 minus E2 equals 0. All right, let me show you why this connects a little more qualitatively. All right. When we take the dot product of our vector n, and the vector n is going to be pointing through the surface. When we take the dot product of n with D1 minus D2, it's going to pick out changes to D specifically of the component that's through the vector, because that dot product is going to isolate only the component that's through the boundary normal. And so that dot product is basically isolating this perpendicular component right there. The cross product is different. The cross product only picks out components that are perpendicular. So n hat cross with E1 minus E2 is only going to look for changes in the electric field that have a component that is parallel to the boundary or along the surface of the boundary. And that corresponds to the tangential component. So that's why we got an n hat cross E1 minus E2 equals 0. So these two are what we call boundary conditions. And they basically allow us to relate the electric fields on one side, the electric fields on the other side, and the charges that are building up at the boundary. Right now, we can simplify this problem if we know something else about the material. So for example, if 1 and 2 are dielectrics only, that is to say they have no conductivity, then we can take that to mean that rho s equals 0. And that greatly simplifies things. All right. We can also say that if 1 is a perfect conductor, for all intents and purposes, for most of the time, a metal, then we can also say that E1 equals 0. And the same, if material 2 is a perfect conductor, then we know that E2 equals 0. So this helps us simplify if we know something about the material. But a lot of realistic materials actually have both dielectric and some conductivity to it. So you can't immediately dismiss that. But if we think about this as, go back to Poisson's equation from, from the last video. If I have a boundary between two materials inside of the space that I'm solving for, I need an extra set of equations in order to relate charges to voltages. And boundary conditions is exactly what's going to give that to us. And we're also going to encounter this as critically important when radio waves sort of strike surfaces. So anytime a radio wave bounces off of like an airplane, for example, in a radar system, we're not going to be able to understand how the radio wave interacts with that metal surface on the airplane until we understand how fields interact with boundaries. And that's what these boundary conditions are going to give us. So this is a building block toward understanding reflections of radio waves off of objects that we're going to see later. And in fact, in a later lecture, we're going to talk specifically about the same equations for magnetic fields. They're going to look similar, except there's going to be an extra complication that's thrown in, that we'll throw in there. But these are what we might call electrostatic boundary conditions. And I call them electrostatic because they specifically apply for static conditions when things are not changing with time. All right. In the next video, I'll give you a couple of quick examples of how we might apply boundary conditions to determine electric fields at interfaces between two different materials or two different objects.